Okay. Okay. Yeah. Great. Today we will be on the chapter 3 about differentiation. Okay. So, well, the calculus is mainly about the differentiation and integration. And now finally, we are ready to discuss the differentiation. So speaking of differentiation, so let me try to remind you the basic definitions of the differentiation. So for the single variable functions, we should remember this was the definition of the differentiation. So fa plus h minus fa by h. And if this limit exists, then we said the function f is differentiable at point A. Okay, good. In other words, I want to rephrase this definition like this: fa plus h minus fa, but I want to bring this guy to the other side of the equation, and minus f prime a times h, everything by 0 as by h is tending to 0. So therefore, okay. So why is it a big deal? Because, well, since h is tending to 0, so in order this limit to exist, then the numerator, since denominator goes to 0, therefore the numerator also goes to 0, right? So that means as h is really close to 0, then this guy should be tending to 0. Therefore, minus fa minus f prime a times h is, well, almost equals to 0. Yeah. So I don't really like the expression, but well, okay. So yeah, I really want to feel. So I really have to use the big O notation, but yeah, I won't. Maybe, yeah. Okay. So, please allow me to use this notation. Yeah, this means approximate. So this guy, this one approximate this one. So, hey, so this side of equation. So what is this? This is f is generally a not necessarily linear equation. This is just a possibly not. This is the nonlinear equation, and the other side of the other side of the equation is a linear equation, linear function for h, right? So, so this is not necessarily linear, but this is a linear function. So, I believe this gives us the idea why we should be focusing the differentiation. Because, well, as I told you many times, being a computation of being able to compute a function usually is a very complicated. This is not an easy task because especially when your function is a nonlinear function. Well, suppose that later on you may want to deal with some other highly non-trivial but very important function. such as, well, maybe the Bessel's function, Airy's function, all those functions. All these functions are defined just by using some solution of very complicated differential equation. And how would you compute that? And computation of such a function is really important, especially in engineering, but turns out to be not an easy task. Why? Because in order to solve the equation, first of all, you will need to solve the differential equation. All right. But this gives us this gives a very nice approximation of this nonlinear. So if you can differentiate your function, then that is going to give you the very nice linear approximation of function. And computation of the linear function is way easier than the computation of it. Right? Okay, so this is why we should be focusing on the differentiation. So I guess you have seen this equation before. So this was what? This is sometimes called the equation of the tangent line at a given point. But for our purpose, I want to call this function as a linear approximation of your original function f at the point A. This is a linear approximation of function f at point. Okay, so basically, this was the basic theories involved for the single variable differentiation of the single variable function. And today, now we'll be turning to more differentiation of the even more complicated functions. But okay, I don't want to make our lives too much complicated. So therefore, for today's lecture, we will be only focusing on the function from R2 to R. And we have this definition. Yeah. We have a function f, and f is a function from R2 to R, right? Yeah. So even though this is, it does not mention explicitly about the codomain of function, but yeah, this is a function from R2 to R. And we say this function is differentiable at this point if this guy k can be well approximated by linear function L in the following sense. Okay, so just forget this. So this function f is differentiable if and only if the limit of this guy is tending to 0 as the length of this vector h, k is tending to 0. Okay, yeah. If you do not know the differentiation of the multivariable function, then this definition might look very complicated. But however, let me try to compare this definition with this. This was our definition of being differentiable of a single variable function at point A. So f is differentiable at the point A as if this guy is tending to 0 as h is tending to 0. Right? Okay. Okay. Now take a look at this, and also we take a look at that. The only difference is, so this is a single variable function. This is a two variable functions. So therefore we had only one variable h, but now we have two variables h and k, and this is the original function minus the point that we are interested in. So this guy minus this is, well, and I told you this is a linear function, right? And L is the another linear function. And if you can find such a nice linear function, and I want to talk about a little bit more about this linear function. And it says this linear function is approximating which one? Which guy? This linear function L is approximating this guy between these parentheses. And this function is what? This function is a function from R2 to R, right? Therefore, this L must have the same domain and codomain just as this guy, right? So L is a linear function from R2 to R. And if you can find such a nice linear function, and so that this everything is tending to 0, as the length of this vector is tending to 0, then finally we can say our function is differentiable at this point. So can you see the similarity between these two? Yeah, I hope so. I hope you do. Okay. So this is the function. I want to say a little bit more about on this linear function. And L, this is linear function from R2 to R. This is linear. And do you remember this? I hope you remember this. And every linear function from R2 to R can be written like this. Can be expressed as a dot product with some other two-dimensional vectors. So, I mean, every linear function from R2 to R, then there is two real numbers, P and Q, such that L of H and K can be written as P times H plus Q times K. This must be possible. So every linear function must be written like this. We know this. So we proved this long time ago. Okay, so and also for now, from time to time, some authors they want to say A plus H is the X, B and B plus K is Y, because this is the X coordinate and this is the Y coordinate. So I want to, so just as we have defined the linear approximation of function at A, so we can do the same thing for these two variable functions. L, X, comma Y. We want to define a function which is f a b plus L H comma K, but H is X minus A minus X and K is B minus Y. So instead of writing like this, so X minus A and Y minus B. And but L can be written as P H top plus Q times K. So this is P X minus A plus Q Y minus. So, okay. Now I also want you to compare this equation with that equation. This equation is called the linear approximation of function f at AB. Okay, All right. So this is what this guy is approximating f x comma y. Right. Okay. All right. It's just because, well, we know that this equation was approximating f of x, right? This, and this equation is approximating f x comma y. Okay. Because, well, this guy is tending, well, this guy is tending to 0 means that the numerator should also tends to 0. Therefore, numerator tends to 0 means that this guy plus this must be approximating this. And a plus h and b plus k is fxy. And so therefore, this guy must be black. Okay, so just as just like the single variable function, so we can argue the same thing. So why do you need to focus on the two variable functions, the differentiation of the two variable functions? That is, the main reason is if you can find such a nice linear function that tends everything to 0 as hk tending to 0, then that means we can actually have a nice approximation of this possibly nonlinear function by some constant plus linear. And as always, computation of the linear function is way easier than the computation of the nonlinear function. Okay. All right. All right. Oh. So this is our definition, but our textbook, they are trying to rephrase this definition something, well, using the vector notation. Let's say that the vector A is the point A comma B, and the vector H is the two-dimensional vector HK. Then this guy, then this is, and this is what? This is large A plus H, and this is A, and this is H, right? So this definition can be written like this. This is our another version of the being differentiable. We have a function f from R2 to R, and we say this function is differentiable at this point A if the limit of this guy tends to 0 as h is tending to 0, right? So, and if it, well, therefore, in order to say if any given function is differentiable at any point, at some point, then the most important one is you must be able to find this nice linear function L, which is approximating fa plus h minus f. So you must be able to find such a nice function. Okay, so what is this guy? Suppose the function f is given. Given your function f, how would you find this linear function? So we want to talk about how do we find this function. In order to do that, first I want to say what do I mean by the limit of two-dimensional two variable functions? Suppose that we have a random function. Suppose that we have some function. This function whose domain is R2. And if you want to discuss the limit of this multivariable function, I hope you understand this first. Well, and this definitely, well, it looks like so as h is tending to 0, the limit of this function goes to L. So that means, so, well, my point h must be tending to the origin, right? But there are so many different ways to tending that is tending to the origin. Well, what do I mean by that? So, in order to observe the limit of this function, then I will need to see the behavior of my function g as h is tending to 0. But there's infinitely different ways that h is tending to 0. Well, h may tends to 0 in this way, following this route, or h can tends to 0 following this route, or h can tends to 0 following even crazier route like this. And in order to say that limit of this guy equals to L, then no matter which route you have chosen, but the limit of your function must almost be the same, right? Always equals to L, right? You have to remember this. So, okay, so I want to find, because using this observation, I want to find out this function L. And what do I mean by finding this function L? Finding L, and every linear function can be written as ph plus qk. Therefore, so finding L is nothing but finding these two constants, p and q. So first, we were supposed to find these two numbers, p and q. So what is p and q? All right. Let us suppose that our function is differentiable at the point A. Suppose that f is differentiable at point A, comma B. Then f A plus h b plus k minus f a b minus LHK, and denominator is h squared plus k squared. Yes, this is the length of the vector h comma k, right? This guy must be 0 as the length of this vector is tending to 0. Oh, hold on. Yeah, I changed my mind. So I want to replace this by ph plus qk. So if f is differentiable at this point, then this limit exists, and the limit equals to 0 as this vector, length of this vector tends to 0. And the vector is tending to 0. This means no matter which route you have chosen, you are supposed to get the same answer. The limit of this expression always must be 0, right? So therefore, I want to consider two routes. So what are these? What are these? The route number 1 is this. I'm gonna choose this direction. this route, I will say route number 1. And the another direction is this, tending to 0 by following the y-axis. I'm going to call this guy the route number 2. Then, if the limit of this guy equals to 0, then following this route, then the limit of this one should be 0. And following this route, the limit of this everything also must be 0. Right? So, number 1, we are going to see what happens if we follow the route number 1. Okay. Route number 1 is the following the x-axis. In other words, this route can be characterized by setting k equals to 0 and h is tending to 0, right? Okay. So then now, even under this assumption, this limit should be 0, right? Therefore, now this expression becomes f a plus h b minus f a b just carries over minus ph by absolute value of h, right? Okay. So as h is tending to 0, and since the limit of this guy, even if I follow this route, the limit of this expression must be 0. Therefore, limit of as h tends to 0 of this whole expression must be 0. Because why? Because this limit must be the same as this limit, right? Okay. All right. But yeah, here I'm going to use a little trick. A limit of any expression tending to 0 is the same as limit of the same expression, but with this one additional absolute value also must be 0, right? Limit of some expression equals to 0 means the limit of the same expression with absolute value equals to 0. They are all equivalent, right? But yeah, well, and for the denominator, I don't need to bring two same absolute values. So I guess I am good to just ignore this h. And so this guy equals to 0. The limit of this guy equals to 0 means, well, I'm going to just get rid of this absolute value just one more time. Yeah. So because by doing so, I just got rid of this absolute value on the denominator. And this is what? F A plus H B minus F A B over H is P. Okay. We just ended up with this expression. Oh, now it gives us the idea. How do you find this number P, this constant? So what was this constant? Well, these two constants, P and Q, these two numbers, they actually characterize the linear function L, right? And the first number, P, can be obtained by, Now take a look at this expression very carefully. And this expression looks very much like to the usual differentiation. So, but the only difference is, well, here the y coordinate has been chosen, was fixed as a b, but the only x coordinate being differentiated, right? So this is, therefore, this is what we call the partial differentiation. So from time to time, we say this fx ab, or denoted by partial f and partial x at a. So this is what we call the partial derivative of f at a comma b with respect to x co. So this is the partial derivative. Okay. Okay. So this is the explanation for the constant b. Okay. Now, how do we get the second number q? So same thing, but in order to get q, we are gonna choose the different route. Instead of choosing route number 1, now we wanna choose the route number 2. The number 2, which is tending route following the route number 2. This route number 2 is now characterized by k is tending to 0 and h equals to 0, right? So because of the same reason, using the same analysis, now h equals to 0 and b plus k, and not ph but minus qk with absolute value of k, and as k is tending to 0, we require that this limit also equals to 0, and but equivalently, this is the same as removing this absolute values for the denominator from the denominator, and this is the same as fa comma b plus k minus fab over k is q. So this is almost, I just ended up with just almost the same equation as before. So compare this with this. So previously, so we consider the y coordinate to be fixed, and we just take a differentiation only for the x variable. And now, in order to get q, we are going to do the opposite. Now, the x coordinate, which is a, is fixed, and we are taking the derivative only for the y coordinate, right? So, and this number is called, denoted by, like this, partial f, partial y at ab, and this is called the partial derivative of f at the point AB with respect to the y value. Okay, all right. So, okay, all right. This is how you get these two numbers. Okay, okay, and how do you know these two limits exist? Because we are assuming that f is differentiable, right? Okay, so that means if we know, suppose that you have some two variable function, and if you know your function is differentiable at some certain point, and then finding these two numbers or find this linear function L is actually very easy. Well, because in order to find these two numbers, then all you need to do is just apply the regular differentiation techniques that you have studied from in the freshman calculus for your function f, right? But so precisely, so in order to get p, then you consider the y coordinate constant, and you only need to the differentiation for the x coordinate. And to get y, you consider the x coordinate fixed, constant, and you apply the differentiation for only for the y variable. Then that is how you get this number q. So once you get these two numbers, then everything is very obvious. Now then you can finally get the linear approximation of function at any, right? I mean, the point here is find the partial derivatives is not a big deal. Is a do-over computation. Mm. Yeah, this is a example from our textbook. And this is the function, and we have a point, and we are supposed to find fx and the partial derivative of x and partial derivative with respect to y at this given point. Mm. Okay, but finding partial derivative is not a big deal. Because, okay, first we try to look for fx, which is the partial derivative of f with respect to x, but which is easy because all you need to do is consider y as constant and take a derivation only for the x variable. So this is going to be y squared because taking derivation for x and derivative of x is 1. So just 1 times y squared, which is y squared. And fy, which is the same thing. Now, x is considered a constant, and you take a derivation for y variable. So this is going to be x times 2y, so which is just 2xy. So fx and fx 1 comma 3, which is also, or you can also easily get these two numbers by plugging x equals to 1 and y equals to 2 for this function. So this is 9, and fy 1 comma 3 is you plug in x equals to 1, y equals 3 into this expression, and you get 6. Okay. 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 All right. And yeah, so this is the end of this. This is solution of this exercise, but I want to do just one step more. So I will try to find the function, the linear approach, the function Lxy in this case. So the L h comma k, which is just p h plus q k, but our notation convention is p is partial f partial x at 1 comma 3, and q is partial f partial y 1 comma 3 by k, and well, yeah, I am intentionally making things more complicated. Sorry about this. Yeah. but H and K, yeah, the same. They are the same thing. So this times this plus this times that. Yeah. So this expression can be factorized by using these two matrices, and this is 9, 6, uh, H and K. So this is how you get your function L. Well, I mean, this is very easy computation. So if you do the fractional calculus, then if you do the differentiation from the fractional calculus, then you can easily find the function L H by using the partial. Okay. Mm. All right. So, I mean, the point is, okay, provided that you know that you already know your function is differentiable at any given point, then finding this function LHK is not a big deal. But the problem is, how do you prove that any given function is differentiable? Yeah, this is somehow very complicated test. I want to show that. Yeah, what was my function? My function is x times y squared. Yeah, x times y squared is differentiable and what is my point was one. Okay. All right. Show that my function is differentiable at the point. Yeah. This requires some sort of serious analysis. Uh, yeah, sounds very scary. Uh, all right. Okay. So, in order to see that this function is differentiable at this point, okay, now I go way back to the definition. Then I will need to verify that this guy is tending to 0 as h tends to 0, right? This is what I'm supposed to show. And I will need to find this function L, right? But we already showed that if the we have already showed that if this guy is differentiable at this point, then my L would look like this. Okay. So if my function is differentiable, then LHK is 9H plus 6K. And we want to show that the limit of F 1 plus H and 3 plus K minus F1 comma 3 and minus LHK, which was 9H plus 6K. Everything by HK. I want to show this. So this is the limit of two variable function. Okay, right. I think I'm gonna do some sort of the epsilon and delta. No. Well, not exactly epsilon and delta, but I want to find a very nice upper bound of this, and if I can show that this upper bound is somehow bounded by length of this vector, and I guess I'm done. So we have this, and this is f1 plus h and 3 plus k, which is squared, minus f1 comma 3 if I plug in x equals 1 and y equals 3, then which is 9. And minus 9h minus 6k, everything by h squared plus k squared with square root. Yeah, we have this such an ugly expression. So it looks like yeah, k squared plus 6hk plus h times k squared. Okay, with absolute. Okay, so we somehow ended up with this expression. And this is we have two terms with k squared. So 1 plus h times k squared plus 6hk so I can rephrase like this. And because of the triangle inequality, so 1 plus h times k squared plus 6h times k. Yeah, I would just say hk. And by square root of h squared plus k squared. Okay. This is going, and well, here, so I want to assume something. I want to assume that the length of this vector is less than equals to 1, because since we are talking about the case when the length of this vector is very small, so it is very reasonable to assume that the length of this vector is less than equals to 1. Then in this case, the length of the first coordinate also must be less than 1, right? Because, well, if hk equals, well, that means if this is hk plane, then we are talking about we are only assuming that when the vector vector h comma k lies inside of the circle, and in this case, the h coordinate must be always less than equals to. So then this one, which is obviously less than 1, so everything is 2k squared plus 6 hk divided by this. And I'm gonna do this. h minus k, everything squared is h squared plus k squared minus 2 times hk. And this is clearly greater than equals to 0. And this implies 2 times hk is less than equals to h squared plus k squared, right? So therefore, 6 times hk is less than equals to 3 times h squared plus k squared. So this is 2k squared and plus 3 times h squared plus 3 times k squared. Everything by this. Yeah. I'll just simply put that 3 times h squared plus 5 times k squared. And obviously 3 is less than equals to 5. So this is less than equals to 5 times h squared plus k squared. And which is less than this. So, and this is 5 times square root of h squared plus k squared. Okay. Wow. Yeah. So okay. So this is what we want. This is what we want to prove, right? But the limit. I will just copy and paste. The limit of this guy is less than equals to. This one just carries over. But we proved that this expression is less than equals to 5 times square root of h plus k squared. So is it 5 times square root of h squared plus k squared? But you know this is what? This is precisely the length of the vector h and k, right? And clearly the length of this vector is tending to 0. Therefore, this guy should be tending to 0. And well, and also this is an absolute value. So this guy, if this exists, then this one is always greater than 0. Therefore, because of the squeeze theorem, the limit of this guy also must be 0. Okay. Wow. Okay. Now the question is, are we supposed to do this kind of analysis in the exam or quiz? And my answer is no. Yeah. I told you this is not an easy test. So I do not require this kind of analysis by yourself. I just want to show that being able to prove any given multivariable function is differentiable at any given point is not a trigger. Okay. Now, I have another function. So what is it? So it looks like this is two variable function, and its output is just a one real number. So this is a function from R2 to R. And I want to show that this function is not differentiable. At the origin. All right. Okay. All right. in order to show that this function is not differentiable, then I want to show that, okay, the limit of this guy does not exist. And in order to discuss the limit of this guy, then first of all, I will need to find this one first. LH. And to find LH, first I will try to find the partial derivative of my function at the origin. And by definition, the partial derivative is h and 0 minus f0, 0. Everything by h. This is the partial derivative with respect to x. I'm just using the definition, right? And f of 0 and 0, which is obviously 0, okay? And as h is tending to 0, this is h minus absolute value of h over h. And therefore, obviously the numerator equals to 0. So the limit exists and the limit equals to 0, right? Okay, now for the another partial derivative, I'm going to do the same thing. And f0 and 0 plus k minus f0 and 0 and everything over k. And this guy equals to 0. Yeah, so I am going to ignore this. And 0k and x equals to 0 and y equals to k. So plugging those in. So I have, as k is tending to 0, so absolute value of k minus of absolute value of minus k. And everything by k. Right? Right? Yeah, but so this negative sign can be simply ignored because we have the absolute values. So this is just absolute value of k minus another absolute value of k. So this guy also equals to 0. So the limit is So we now have these two partial derivatives. So now we consider this limit. H and k. So this vector is tending to 0. And f0 plus h and 0 plus k minus f0 minus the LH. But these two partial derivatives, they are both equal to 0. So this is what? This is just simply 0 times h plus 0 times k. So this guy is obviously 0. So, and we have h squared plus k squared on the bottom. But now, if the limit of this guy exists and this limit equals to 0, then this function is differentiable. But I want to show that this limit of this guy doesn't exist. Well, see, because this is the limit of two variable function, so therefore, if the limit of this guy exists, then this is the h and k plane. And the vector h, k is now tending to 0. And there are infinitely many different ways to different way that h, k, k is tending to 0. But I'm going to show you we have two different routes. And I'm going to show you that if I choose this route, then the limit of this guy does not equal to 0, right? Okay, then it proves that the limit of this guy never equals to 0, right? I mean, so if you can find at least one path such that whose limit is not equals to 0, then that proves that the entire limit cannot be. Okay, so let me follow this route. If h and k they are the same numbers, then this condition that the length of the vector h comma k tending to 0 is equivalent to the k equals to 0, and fk comma k minus f0, and which is square root of 2 times absolute value of k. And this is what? So this is k minus k. So this is limit k0, and I plug these two numbers into the x and y's, and we have absolute value of 2 times k. And plug in here, then you get 0. And this is square root of 2 times absolute value. So which is just square root of 2. And this guy, the number, is not 0. So I was able to find one route such that whose limit is not equal to 0. Then therefore, this proves that this limit never be. Okay. Okay, so today we spent one entire lecture just to discuss if any given function is differentiable or not. And as you can see from here, so being able to show that any given function is differentiable at any given point is way too much complicated task for us. But there is a good news. What is that? So f are continuous, and open set contains AD, then f is automatically differentiable. This is so nice. This is so nice here. All right. So first, I want to explain this statement. And this is the assumption: the partial derivative of f, they are continuous. Okay. So generally speaking, for any given real value function from R2, two variable real value function, and their partial derivatives are also two variable real value function, right? So why? Because, well, from this picture, yeah, from this example, this is a function from R2 to R, and their partial derivatives are, the one was the fx is y squared and fy is 2xy. So these partial derivatives are also two variable function, two variable real value function. And we are assuming that these two partial derivatives of f, they are both continuous on an open set containing this. So here, okay, so works. And if you take a look at this, these two partial derivatives, they are just nothing but polynomials, right? And polynomials are automatically continuous. Right? You don't need to prove the continuity of the polynomial because you know the function. You know this function is continuous, and you know this function is also continuous, and you know product of two continuous functions is also continuous. So you don't need addition of two continuous functions is also continuous. Therefore, these two partial derivatives, they are very well behaving continuous functions. Therefore, and if you believe in this theorem, well, then since our partial derivatives are continuous on an open set containing 1, 3, therefore, my function is automatically differentiable. Right? So that means actually this entire analysis is not needed. Why? Just by looking at their partial derivatives and you know they are continuous, so you're done. Isn't that great? 너무 괜찮지 않아요? 이게 원래 사실 제가 정규 여기 calculus 2 강좌에서는 이걸 증명하는데 시간을 많이 쓰도록 하겠지만 이번 코스에서는 제가 완전 재량권을 썼기 때문에 증명을 생략하고 넘어가도록. Okay. You just trust me. This is true. Okay. 뭐가 좀 좋은 것 같죠? 여러분 믿으십니까? 네, 저를 믿으시고 저는 이걸 증명하지 않고 넘어갑니다. 그래서 이제부터는 어떤 함수가 이제 특히 우리가 보통 소위 말하는 elementary 펑션들의 조합으로 만들어진 함수입니다. sin x 제곱 더하기 y 곱하기 sin xy 뭐 이런 거 아니면 로그 x 더하기 y 뭐 이런 함수들이 뭐 주어진 포인트에서 미분 가능합니까? 안 합니까? 라고 물어보면 여러분들 굳이 고민할 필요가 있다 없다? 없다. 있는 거죠. 걔네들의 파셜 디리버티브를 보고 파셜 디리버티브가 주어진 오픈셋 내에서 우리가 궁금한 포인트를 포함하고 있는 오픈셋 내에서 모두 연습함수인 것만 확인되면은 끝! 더 이상 우리가 할 필요 없어요. 되게 좋은 걸 했고요. 다음 제가 시간이 5분밖에 안 남았는데 다음 시간에는 이제 가변수 함수의 미분 가능성에 대해서 제가 이야기를 하도록 하겠습니다. 오늘은 여기까지 하고 넘어갈까요? 네. 오늘은 5분만 일찍 끝낼게요. 수고하셨어요. 네. 네.